Hello biology students, we're going to talk about biological chemistry today. This will be the first of two lectures covering biological chemistry. So biological chemistry mostly focuses around the topic of organic chemistry. And organic chemistry is not too hard to understand. It's the study of chemistry involving the element carbon, as you can see over here, carbon. We haven't talked too much about carbon yet, but suffice it to say that carbon can make 4 bonds. Carbon has 4 active sites, so to speak, in its valence shell of electrons, so it can make 4 bonds. That versatility is what makes carbon such a common element. So we talked about how water is maybe the most important molecule for life on this planet, but I would say carbon might be the most important element for life on this planet. Nearly every molecule in your body, aside from water, contains carbon. The two examples of carbon molecules that we wouldn't call organic would be carbon dioxide or carbon monoxide. Those gases we just consider regular molecules. But you're going to see that many types of molecules that are very common to everyday life are called organic molecules, meaning that they have a backbone of carbon. Okay, I'm going to talk about some types of molecules called hydrocarbons. They contain carbon and hydrogen. They don't have any polarity, so they usually will not mix with water. And we've talked about this notion of entropy, or maybe we haven't. Entropy is that things tend towards disorder. So for instance, if you clean up your room, it'll tend to get kind of unclean pretty quickly. Now partly that might be because you're messy. The other part of it might actually just be if you left your room for 50 years, it would get dusty and nasty on its own. Things really in life tend towards disorder unless you do work in order to organize them. Now, energy is the ability to do work. So usually you apply energy in order to build things. And usually things tend to fall apart on their own. So the general process in life is you apply energy to build things, and then you continue to apply energy to keep them up, to keep them really from decaying or decomposing or deteriorating in some sort of way. You could think about a house like that, but you could also think about life like that. So as long as a human is able to keep living and intaking energy through the form of food and getting water and keeping themselves up, their body can use that energy to do work to keep their body in good order. As soon as a human dies, they stop intaking energy and doing the work of upkeep, and their body starts to decompose. So this is that notion of entropy. Entropy says that in life, or just in general, most things tend towards disorder. Now, because of that, when you do the work of making a new molecule, you actually can store energy in the molecule. So the energy that you use to do the work of making a new molecule actually stores energy in the molecule. That energy is stored in the bonds of the molecule, and the energy that is stored in molecules is called chemical potential energy. An example of that is gasoline here. This is a gasoline fire, I believe. Gasoline has energy stored within the molecule, and that energy is called chemical potential energy. Obviously, if you release that energy, it makes an explosion in the form of heat. And that heat is actually what causes the expansion of a gas inside of a car cylinder that makes an engine go. Now, another concept that's interesting for organic chemistry is the notion of what are called polymers. P-O-L-Y, that Y is cut off, P-O-L-Y-M-E-R-S. Polymer is simply a molecule that's made of individual repeating units. So a polymer is a molecule made of individual repeating chemical units. The individual chemical units are called a monomer. You can see right here, a monomer. If you put multiple monomers together, you get a polymer. The way that you often put them together is called dehydration synthesis. Synthesis means to make, and dehydration means to take water out. So right here is an example of how if you kind of take the water out that exists here, you can link them together to make a longer polymer. Now, you can also take polymers apart, and that's often called hydrolysis. So, quote, inserting a water. It's not really how you do it, but you insert a water, so to speak, and it breaks off one of the monomers, thereby shortening the polymer. Polymers really are common. A few polymers that we'll talk about are starch and cellulose, but really every rubber and plastic that you've ever experienced in your life is a polymer. So here's an example of dehydration synthesis making maltose. If you get malt powder in your milkshake, that's what the sugar maltose is, and that's by forming two glucoses. So if you take two glucoses together, do a dehydration synthesis, you get maltose. Now here's some other example of carbohydrate polymers. We have starch, which is of course in potatoes and different grains. And then we also have cellulose, which looks awfully similar to starch. So starch is 4 glucose monomers linked together. Cellulose is 4 glucose monomers linked together in a different way. Now cellulose is wood and starch you can eat. You can't eat cellulose, but you can eat starch, and it's just based on how these monomers are linked together to make the polymer. Now carbohydrates are a class of molecule that contain carbon, hydrogen, and oxygen, and they are the primary energy storage molecule for, I think, just about every living organism. So for instance, the main food that you eat for your calories daily is going to be carbohydrates, and that's in the form of starches and sugars and even fibers included within carbohydrates. So bread would be a carbohydrate source, fruit would be a carbohydrate source, pasta would be a carbohydrate source, rice would be a carbohydrate source that's common, potatoes, etc. So carbohydrates are really important. Obviously cellulose you can't eat because you can't digest wood. You don't have the proper enzymes. Now these would be called a polysaccharide. They have got 4 sugars, the sugars being glucose, linked together, polysaccharide. Now if we go back to maltose, maltose would be considered a disaccharide, 2 sugars linked together, disaccharide. Glucose is a monosaccharide. So mono, di, poly. We've talked about glucose. Now fructose is another. So here if we do 2 glucoses together we get maltose. Now if we did a glucose and a fructose, which is similar to glucose together, we would get a disaccharide called sucrose. And sucrose is what table sugar is. So often what they do with sucrose is they'll increase the fructose content and what that's called high fructose corn syrup. It makes it taste a little bit sweeter and maybe potentially makes it unhealthy. The molecule here that makes up gasoline, that stores energy in gasoline, is called octane. You've probably heard of it before. It's got 8 carbons and 18 hydrogens. Octane obviously stores a lot of energy, and that's why it makes good for gas. You've seen the octane ratings on different gasolines, 87, 91, 93. That just refers to what percentage, I think, of the gasoline liquid is octane. So the higher the rating, the more burnable fuel you have within a gallon of gasoline. So that's it for today for organic chemistry, and we'll pick up with the second part of the organic chemistry lecture next.